Today we will explore clustering algorithms in data mining. Continuing our exploration of clustering, let's focus on partitional clustering. This technique is non-hierarchical, meaning each data instance is assigned to exactly one of k non-overlapping clusters. The key here is that the user typically specifies the number of clusters k beforehand. This input guides the algorithm in dividing the dataset into distinct groups, ensuring each instance belongs to only one cluster. This approach contrasts with hierarchical clustering, where multiple nested clusters can exist. Partitional clustering is often used for its simplicity and efficiency, especially in large datasets where a clear partition is desired. Building on our understanding of partitional clustering, let's examine the squared error, a key concept in evaluating clustering quality. The formula for the squared error for a cluster SSE_I is the sum of squared distances between each data points, POC in class D, and the cluster centroid mu_I. This measures how tightly the data points are grouped around the centroid. The total squared error, SSE, is the sum of these errors across all k clusters. Minimizing this cost function ensures that clusters are compact and well separated, which is crucial for effective clustering. The graph on the right visually represents this by showing how data points are grouped around their respective centroids, highlighted by reduced distances. Now let's delve into the k-means algorithm, a fundamental partitional clustering technique. The process begins by deciding on the number of clusters k. Next, you initialize the k cluster centroids, which can be done randomly. Each data point is then assigned to the nearest cluster centroid, determining the initial class memberships. Following this, you re-estimate the centroids by calculating the mean of all points in each cluster. This process iterates, reassigning data points and updating centroids until no data point changes its cluster membership. This iterative refinement ensures that clusters become more distinct and well-defined with each cycle. In step 1 of k-means clustering, we begin by initializing the cluster centroids. Here, 3 centroids, mu_1, mu_2, and mu_3 are placed randomly in the data space. The Euclidean distance metric is used to calculate the distance between each data point and the centroids. This metric helps in determining which centroid is closest to each data point. By evaluating these distances, we can assign points to their nearest centroid, forming the initial clusters. This step sets the foundation for iterative refinement. In subsequent steps, our clusters are adjusted for optimal grouping. In step 2 of k-means clustering, after assigning data points to the nearest centroids, we update the centroids' positions. The centroids mu_1, mu_2, and mu_3 are recalculated as the mean of their respective assigned data points. This adjustment is depicted by the arrows indicating the movement of each centroid towards the center of its cluster. The orange lines represent the decision boundaries separating the clusters based on the Euclidean distance. This iterative process of realignment continues until the centroids stabilize, ensuring optimal clustering. In step 3 of k-means clustering, we observe the updated positions of the centroids wa1, mu1 underscore 1, mu underscore 3 after the previous adjustments. Each centroid is now more accurately centered within its respective cluster. The data points are reassigned to the nearest centroid based on the Euclidean distance metric. This process of recalculating centroids and reassigning points continues iteratively. The goal is to achieve stable centroid positions, indicating that the clusters have reached their optimal configuration. This iterative refinement ensures that each cluster is as compact and well separated as possible. In step 4 of k-means clustering, the centroids mu_1, mu_2, and mu_3 are further adjusted. The arrows indicate the movement of each centroid as they continue to converge towards the center of their assigned data points. This refinement process is guided by minimizing the Euclidean distance between the data points and their respective centroids. The iterative updates will persist until the centroids stabilize, meaning there is little to no movement, and the clusters are optimally formed. This step highlights the dynamic nature of k-means, ensuring precise and effective clustering. In step 5 of k-means clustering, we see the centroids mu_1, mu_3 have reached stable positions, with each cluster distinctly formed. The data points are grouped around their respective centroids based on the Euclidean distance metric, reflecting the optimal partitioning of the dataset. The axes, labeled as expression in condition 1 and expression in condition 2, suggest that the data might represent different conditions or dimensions being analyzed. This final configuration indicates successful clustering with minimal distance between data points and their centroids, ensuring compact and well-separated clusters. In discussing the convergence of k-means, we focus on the cost of clustering, which is calculated as the sum of squared distances between data points and their respective centroids. This cost decreases with each iteration, as observed in steps 1 and 2. Since the cost is always non-negative, it is bounded below by 0. Consequently, the iterative process of k-means ensures that the cost continually reduces until it can no longer decrease, leading to convergence in a finite number of steps. This guarantees that the algorithm will find a stable clustering solution efficiently. This illustration demonstrates the application of k-means clustering in image segmentation using different values of k. As k increases from 2 to 10, the segmented image becomes more detailed, closely resembling the original. With k2, the image is highly abstracted, showing broad regions of color. As k increases, more color variations are captured, enhancing the image's detail. This process also highlights vector quantization for data compression, where lower k values result in higher compression but lower image quality. This technique balances compression efficiency with visual fidelity. Choosing the right k in k-means clustering is crucial. One approach is to consult domain experts to assess the clustering results. Another idea is to optimize the sum of squared errors, SSE, but this isn't practical since SSE naturally decreases as k increases. A more effective method is the elbow solution, where you plot SSE against k and look for a point where the rate of decrease sharply changes, indicating a balance between compactness and simplicity. This helps in selecting an optimal k that maintains clustering efficiency without unnecessary complexity. When k1, all data points are grouped into a single cluster with one centroid shown as the black dot. The objective function, representing the sum of squared distances from the data points to the centroid, is 873.0. This high value indicates significant distance and variance within the cluster. As we increase k, we expect this objective function to decrease, reflecting tighter and more accurate clustering. This setup highlights the importance of choosing an appropriate k to minimize within cluster variance effectively. With k2, the data is divided into two clusters, each with its own centroid. This division significantly reduces the objective function to 173.1, reflecting a decrease in the sum of squared distances from the points to their respective centroids. This reduction indicates improved clustering accuracy compared to k1. By splitting the data, each cluster becomes more focused and compact, of increasing compact clustering efficiency and precision. When k3, the data is further divided into three clusters, each with its own centroid. The objective function decreases to 133.6, indicating better clustering by further minimizing the sum of squared distances within each cluster. This additional split allows for more precise grouping, reducing intra-cluster variance. As k increases, clusters become more specific, capturing subtle variations in the data, which enhances clustering accuracy. However, it's important to find a balance as too many clusters can lead to overfitting. In this plot, we observe the cost function values for k ranging from 1 to 6. There's a noticeable drop at k2, indicating a significant reduction in the cost, which suggests that 2 clusters might be optimal. This method of identifying the optimal number of clusters is known as elbow finding or knee finding. The idea is to identify the point where adding more clusters results in diminishing returns regarding variance reduction, helping determine a suitable K for effective clustering. K-means has several strengths. It's guaranteed to converge, meaning it will always reach a solution. The algorithm is relatively efficient with a complexity of OTcan, where n is the number of objects, k is the number of clusters, and t is the number of iterations. Typically, both k and t are much smaller than enhancing efficiency. Additionally, k-means is easy to implement and understand, making it a popular choice for clustering tasks. K-means does have some weaknesses. It's sensitive to starting centroids, which can affect the final clustering outcome. It's not suitable for clusters with non-convex shapes, as shown in the images where k-means struggles to separate intertwined clusters. You also need to specify k in advance, which might not always be straightforward. Additionally, k-means doesn't handle noisy data and outliers well, which can skew results. These limitations suggest that while k-means is useful, it's important to consider these factors when choosing it for clustering tasks.